Hey everybody, it's Tuesday, October 10th, and today we are going to talk about how we can describe the motion of objects under the influence of gravity. And so I'm sure a lot of this you remember from honors physics, but of course, as is always the case in this class, even when we talk about things that we did talk about in honors physics, we're going to take it to somewhat of a deeper level. And so the first thing we want to do is talk about describing the motion specifically, just using words. And so when we describe the motion of an object under the influence of gravity, usually we refer to it as being in free fall. And so the first thing we want to bring up here is just what that definition is. And the definition of free fall is that when an object is in free fall, the only force acting on the object is the force of gravity. And so the only force that acts on the object is the gravitational force when an object is truly considered to be in free fall. Now, obviously, free fall then, to some degree, is an idealized version of real-life motion. In real life, there are obviously always other forces acting on objects besides gravity, like, for example, air resistance. But regardless, for many objects, since air resistance is not a huge factor, we can say that treating it as just like a true free fall problem is a decent approximation. So when an object is in free fall, we treat it as though the only force acting on it is gravity. And we can do that even when the only force acting on gravity the only force acting on the object that's significant is gravity. So, of course, the next big question we want to ask here is, well, when an object is in free fall and the only force that's acting on it is gravity, how is gravity affecting the motion of the object? And the answer, as I'm sure you remember, is that free fall causes the object to accelerate. And I would imagine most of you even remember the number for the acceleration that we used in honors physics. But what we really want to do at this point is make sure we understand what we remember. And so the first big question that we're going to ask here is, when we were in the first physics class, we said when an object is in free fall, it experiences a constant acceleration. The question we want to ask here is, how do we actually know that that's true? Could we confirm that? How do you know that an object accelerates at a constant rate when it's in free fall? How could you confirm that? And so let's go all the way back to the beginning, thinking about motion and thinking about experiments. How could we perform an experiment without, crazy complicated tools to determine if an object is moving at a constant velocity? Well, when an object is moving at a constant velocity, we know for a fact that if we collected position and time data for this object, the graph of the position versus time would look like this, but straight. It would be a nice constant slope, because for a position versus time graph, the slope represents the velocity. And so the constant slope would show us we have a constant velocity. And that brings us to the question we just asked here, which is, how do you know when an object is in free fall that the acceleration is constant? Well, if we took position data for an object in free fall, then we would get a graph that shows an exponential increase in the position, meaning that the thing is accelerating, right? Because acceleration always produces a curve on a graph of distance versus time. And so we can use this graph of position versus time, definitely to confirm that the object is accelerating. But that doesn't quite show us necessarily that the acceleration is constant. How would we prove that the acceleration is constant? The key lies in the last experiment. As we saw in the last experiment we did, the acceleration is equal to twice the displacement over t squared. And so that means if we take twice the displacement on the y-axis and t squared on the x-axis, if we plot that graph, the acceleration is constant if the line is straight. And the acceleration is the slope. If the line was curved like that, then we would know that the acceleration was increasing because, well, the acceleration is the slope. And if the slope is increasing, then the acceleration is increasing. And so all we would have to do is look at an accelerating object, accelerating due to gravity, and watch and observe its motion and take position and time data. And as it turns out, when you watch an object in free fall like this, you can tell just looking at the thing that it's accelerating. And if you actually take the data, then you can in fact confirm that the acceleration is constant. Now, of course, the question is, well, how can we use this to tell that this thing is accelerating? And the idea is, if you look at each successive time interval, you can see that the distance is getting bigger and bigger and bigger as time goes on. And the distance is getting bigger because the object is accelerating, and that's how we know that it is accelerating. And so here we can actually watch this video. There are a couple things I want to say about it. The first thing we can say is this water droplet in this video is not actually moving in slow motion. There is a flashing light called a stroboscope, which is flashing at a certain rate. If you use the frame rate on the camera and fine-tune the flashing of the lights, basically every time the camera is taking a picture, the light lights up the droplets, and they can be configured in such a way to make it look like they're in slow motion. That's not exactly the point here, but the point is to show that as this thing falls, you can definitely see it's getting faster. We could definitely see that the distance it's traveling each second is getting larger. And if we actually, notice there's a ruler here, if we actually plotted that data on a graph, then we would know for sure that the object was experiencing a constant acceleration. Now that's really all that we have to say with this video, but this part is pretty cool, so I'll just show you this. Now they can change the flashing of the light and slow down the droplets even more, speed them up, make them look all weird, or make them look like they're going backward. Pretty cool. So, big note here. Gravity produces a constant acceleration of 9.8 meters per second squared. What? 9.8? I'm sure some of you are thinking that. There's a very specific reason why I'm using 9.8. And that's because the AP Physics reference table uses 9.8 meters per second squared for the acceleration due to gravity. So notice that number is the first constant that we've seen in the reference table so far, and that number, 9.8 meters per second squared, in this particular reference table is given only to two significant figures. Now, I know some of you are thinking, how am I supposed to remember to write down 9.8? I've been writing down 9.81 for so long. Well, first of all, I understand. We're going to have to make an effort to just write 9.8 meters per second squared now. And you should be able to accomplish that because I teach another class where we use 9.81 and I managed to keep it straight for the most part. And so just try your best to remember that 9.8 is the number we want to put here, and hopefully we should be fine. And the last thing we wrote here is we know this because an object dropped under the influence of gravity will travel increasing amounts of distance in equal amounts of time. Take a minute to pause this video and write that down. When you hit play, we'll talk about the approach to solving problems. So there's really not a whole lot to say when it comes to how you're supposed to approach solving these problems. The main thing to remember here is because free fall is an example of accelerated motion, then all of the equations that we use for accelerated motion apply. Having said that, there is one super important detail for everybody to remember, and that is the sign convention. For free fall problems, we only use vector quantities, where up is positive and down is negative. To be clear, if the problem asks you for a scalar quantity, then you will solve for the vector quantity and then just take the magnitude of that quantity. So if they ask you for speed, you solve for the velocity, and then you just report the magnitude of the velocity. That's how this works. And really, the reason why we're making up positive and down negative is just because that makes sense if you consider a y-axis, right? So if you consider a y-axis, the positive y direction is up, and the negative y-axis is down. And so we're basically just sticking with that scheme. Okay, let's take a look at a problem. This problem is from the 1D motion packet. It's on page 4, number 40. It says, estimate how long it took King Kong to fall straight down from the top of the Empire State Building, which is 380 meters high, and his velocity just before landing. If you think this is a weird problem, it's not that weird, actually. You might not understand the cultural reference. There was a movie, I think the movie was called King Kong, that was released in like the 30s or 40s, where King Kong climbs up the side of the Empire State Building. I'm sure if you Google King Kong Empire State Building, you will be able to see the video. And that's what this is referring to. I think the point was they flew a plane around the Empire State Building where King Kong was currently at the top of in the film, and then he fell. So this is a two-part question. I'd just like you to focus on part A. Take a couple minutes to pause this video here and answer the question for part A. How long did it take King Kong to fall down from the top of the Empire State Building? When you hit play, we'll go over it. Okay. So there are a number of ways that you can do this. Notice, because I just asked you to do part A, really what I was hoping is that you would sort of force yourself to do part A before part B. And the reason why is because the equation that you would use to do part A on its own would be probably the most important equation for free fall. So the first important thing to realize is they say King Kong falls. And when they say falls, they are trying to indicate to you that the object, in this case King Kong, starts from rest. So just to go back to it for a second, they say here, when the object falls, that the object is not thrown with an initial velocity, and so the initial velocity here would be 0. The displacement, notice here, is delta x. You could call it delta y if you want to, because now we're talking about the vertical direction, but we'll just stick with the equations in the reference table and call it delta x. The displacement of King Kong is negative 380 meters. Now, of course, the big question is, why is the displacement of King Kong negative? Well, if this is the Empire State Building and King Kong starts up here and ends up down here on the ground, then King Kong is displaced in the negative direction, down. And so the reason why we call these displacements negative in a free fall problem like this is because the object is always moving down. And if the object is moving down, then we know that the displacement is negative. And then lastly, the acceleration here is negative 9.8 meters per second squared. And we are looking for the time. Now, looking at the list of variables that we have and looking at the thing we're looking for, there's only one equation that suits our needs. And that would be the displacement equation. Delta x equals v naught t plus 1/2 at squared. This equation is your go-to free fall equation because the initial velocity is 0. And because the initial velocity is 0, we can get rid of that, which leaves us 1/2 at squared being equal to the displacement. That means because the acceleration due to gravity here is always known, that if you know how high it was, you can immediately find the time it took to fall. And if you know how long it took to fall, then you can immediately find out how high it was. So to solve this for t, we have to multiply both sides by 2 and then divide by a. So we get t equals the square root of 2 times delta x over a. And now here we're just plugging in. So we have 2 times negative 380 meters over negative 9.8 meters per second squared. Now notice, it really makes sense then why that displacement has to be negative. This is usually what causes people to lose points on a test. If you make the acceleration due to gravity negative because it's down, but you forget to make the displacement negative, then you have the square root of a negative number at this step, which is going to give you an imaginary number for your time, which is clearly a problem. So when you do that math, and you take the square root, your answer is 8.8 seconds. Notice here I'm reporting it as 8.8 because 380, the only number actually given in the problem, is given to 2 sig figs. Okay, part B asks you now to determine the velocity of King Kong just before landing. Now, this is an important point because most of the time what I see people doing in honors physics, at least, and that means some of you might have done this or thought this, and so I just want to take a second to address this before we maybe run into the same problem again. A lot of people get confused when they ask this question because they say, well, after the person hits the ground, their velocity is going to be 0. So isn't the final velocity for this problem just 0? Now here they were generous in the sense that they said just before landing. But regardless, free fall is a situation in which the only force acting on the object is the force of gravity. And so if the problem just says determine the final velocity, if you are considering that the fact that the ground is slowing the object down, that means you're not considering a free fall problem anymore, which is not the point of this. So whenever you're asked to calculate the final velocity here in these free fall problems, the answer is not going to be 0. We are considering how fast the object, in this case King Kong, is going the instant before it makes contact with the ground. Because the instant it does make contact with the ground, there will be another force exerted on the object besides gravity, which means it'll no longer be in free fall. Take a couple minutes to pause this video, answer part B here, and when you hit play, we'll go over it. Okay, so here we have to find the final velocity of King Kong just before he hits the ground. Because this is a part B, I'm going to go ahead and treat this as an entirely separate problem and rewrite my known. So I have the initial velocity is 0. The acceleration is negative 9.8 meters per second squared. Now, in my opinion, there is one equation that you could use here that is significantly easier to use than the only other equation that would allow you to answer this. Having said that, because I think it'll be valuable to see, I want to actually show both of them. And so the first one I'm going to show is the one that I think is definitely easier, which is making use of the time we just found. And the time we just found is 8.8 seconds. And we're looking for the final velocity. So if we have the initial velocity, the acceleration, the time, and we're looking for the final velocity, then the equation we want to use here is Vf equals V naught plus At. Again, the initial velocity here is 0, and so that means the equation just reduces to A times t. Remember, A times t is really telling you the change in velocity. And if the object started from rest, then the final velocity is just going to be however much the velocity changed by. So we plug in our acceleration, negative 9.8 meters per second squared. We plug in our time, which was 8.8 seconds. And our final velocity comes out to be negative 86.24 meters per second. But again, because everything in this problem should be given to 2 sig figs, we'll call it negative 86 meters per second. Notice a couple things here. First, using this equation, it is simply a consequence of the math that the answer works out to be negative. Like negative times positive is just a negative, it's a fact. But it also makes good physical sense based on the sign convention that we developed right before we solved this problem. If something is up, it's positive, and if something is down, it's negative. And in this case, the velocity of the object is certainly down. But I'm sure some of you probably solved this using another equation, and so that's what I want to address, because this one is tricky, and sometimes you have no choice but to use it, and so I think it would be worth going over. So the other equation that you can use here is the time-independent equation, because that equation is solved by default for Vf squared, and so we can use that to solve for the final velocity if we use the displacement. And the displacement given in the problem, remember, was 380 meters. And notice I made the cardinal mistake of freefall problems. It's very easy when you're rewriting these variables to forget negatives. And so you want to just make sure you go back in there and add the negative sign to whatever you're writing, because it's going to mess you up. Now, luckily, as you're going through the problem, you should be able to catch yourself if you're being careful. So the time-independent equation as printed in the reference table is Vf equals Vf squared equals V naught squared plus 2a delta x. Remember, in the reference table, it's shown as x minus x initial, but that is delta x, so you can just write that in there. And like we said, the initial velocity is 0, so we can write this equation as Vf squared equals 2a delta x, or if we just take the square root, which you can do that on the same line if you want, we get that the final velocity is 2a delta x. And plugging that in, we get 2 times negative 9.8 meters per second squared times negative 380 meters. And this is what I meant before by hopefully you would be able to catch your mistake if you were paying attention. that if you only had one negative number under the radical, you'd have a problem because your answer would come out as an imaginary number, and it should be obvious to everybody why that's a problem. And so the negative times the negative under the radical gives you a positive, so we have no issue. And when you do 2 times 9.8 times 380 in your calculator, forgetting the negatives because they cancel, you get 7,448. And when you take the square root of that, you get 86.30. But it's important for everybody to remember, it only makes physical sense if the final velocity is negative, because it's going down. And my calculator just says 86.30. You have to remember here that when you take a square root, your answer is plus or minus 86.30. And so now you have to evaluate which answer makes sense. And the answer that makes sense here is negative, right? Think about it. This object is being accelerated down, and it's falling down 380 meters. And if you put that the answer is after falling down 380 meters, the object is going up with a velocity of almost 90 meters per second, that's insanely wrong. Now, you don't need to write this plus or minus here, but you have to remember that whenever you're taking square roots in this class, that the answer is technically both positive or I should say either positive or negative from the square root, and you need to pick which one is the most appropriate based on the problem you're solving. And in this case, the most appropriate one based on the problem we're solving is negative 86.30 meters per second, or to 2 sig figs, negative 86 meters per second, which notice is the exact same answer we got for the last one. And so let's just take a moment to write a quick little note about that, because that's very important. When taking square roots to obtain final answers, you must remember that the answer from a square root could be positive or negative. Your job is to evaluate the situation to determine which answer makes physical sense. Notice some of you who are thinking, being careful and aware, are probably just thinking, didn't we have that issue come up already in this problem? Because didn't you take a square root to find a time? Yeah, I did. But we don't really think too hard about it when we do that, because a negative time makes absolutely no physical sense. Just like it doesn't make any physical sense for an object that is falling down for 380 meters to end up having a velocity that's up. Take a second to write that down, pause the video here, and when you hit play, we'll move on. Okay, and that brings us to a question that usually I have you guys break up into groups and discuss. Of course, because we're not together, you'll just have to take a moment to pause the video and think about the answer to this question. Here is the question. This notice is in the 1D motion packet, page 1, number 11. It says, as a freely falling object speeds up, what is happening to its acceleration? Does it increase? Does it decrease? Or does it stay the same? For part A, you're to ignore air resistance. And for part B, you're to consider air resistance. Interesting. I want you to just pause the video here for a couple of minutes, like 2, and think about it. Don't write anything, because I'm actually going to summarize the answers here after you hit play. But I'd like you to pause the video and just consider the answer to this question here. Does the acceleration increase, decrease, or stay the same if you ignore air resistance And what happens when you consider air resistance? Take a couple minutes to think about this. Pause the video, and when you hit play, we'll go over it. Okay. So first we'll talk about A, then we'll talk about B. For A, I think the answer here is pretty straightforward. Having said that, there is a very specific reason why they ask this in like basically every intro college physics textbook. It's because most intro to physics college students end up mixing up acceleration and velocity. Yes, it is true that when an object is in free fall, its velocity increases, in magnitude at least. But velocity and acceleration are not the same thing. Acceleration is the rate at which the velocity increases. And if you ignore air resistance, which we are going to do for part A, then we can say here, when air resistance is ignored, the acceleration of an object in free fall is constant, meaning the velocity increases at a constant rate. We know what that rate is. It's 9.81 meters per second squared. And I'll put the negative sign in there too, because we probably should. I did say velocity. And so that's part A. When air resistance is ignored, the acceleration of an object in free fall is constant, meaning the velocity increases at a constant rate. But what about B? B says to consider air resistance. Well, this requires a little bit of understanding of forces, and we didn't really get to that, but we did talk about that in honors physics, and so I hope that this will make sense to you. When an object is in free fall, and the only force that's acting on it is gravity, it has one downward force acting on it, and that force, as we said, is gravity. But if there's air resistance, like all friction forces, acts in the opposite direction of the object's velocity. And so the force of air resistance, which I'll just call F air, will be up because the object is moving down and the air resistance always acts in the opposite direction of the velocity. And so the point here is the net force, which is going to be the sum of Fg and F air, which in this case is actually negative because it acts the other way. Or you can consider the force of gravity negative. Either way, they're opposites, so you would subtract them. Means that the net force in this situation is actually going to be less than Fg. And since forces cause acceleration, that means the acceleration due to gravity is going to be less than the acceleration in a situation where there's air resistance. And so what we're going to say here is that when there is air resistance, since air resistance opposes the motion, so when there is air resistance, since air resistance opposes the object's motion, the acceleration of the object decreases. Now, here's the deal. Kids usually get confused about this part. If the acceleration of the object is decreasing, then what happens to its speed? The most common answer to that question is that it decreases. It does not. Acceleration, at least for the purposes of free fall, when an object is just literally falling from rest, the acceleration is telling you really how much the speed is increasing by. So if the acceleration decreases from 9.8 to 8.8, it doesn't mean the speed is decreasing. It means the speed is increasing just by a little less each second than it was before. And so what we'll say here is this means the velocity of the object is still increasing, but it is increasing by a smaller amount each and every second than it would be if there was no air resistance. Take a second to pause this video right here and write that down, because that's a very important point. And when you hit play, we'll look at some graphs. Okay, so let's go ahead and take a look at some graphs. These are what the graphs look like for free fall. So starting from the left, we see here that the velocity graph shows free fall. How? Because the velocity versus time graph has a slope which is equal to the acceleration. And so notice the acceleration is supposed to be a constant and negative 9.81 or 9.8. See, I did it there. A constant and negative 9.8 meters per second squared. We see that the slope is a constant negative value. Notice the acceleration graph, super straightforward, just showing you a constant negative value the whole time. And for the position graph, we see this downward curve like this. And essentially what they're showing here is the object in free fall, because if we looked at the slope of the tangent line, it's getting larger and larger, but in the negative direction, meaning that the velocity is increasing as time goes by. Now, it's important to note, I just want to draw this over to the side maybe a little bit. In this particular image, they're showing the initial position of the object as being some positive number and the ground as being 0. Usually I make the initial position 0, and that will just be located wherever the object is, and whatever else is underneath that is underneath that. And so it'll be negative position territory, but it's important to realize it could, sorry, this pen is being really glitchy right now. It could also look like that, starting from 0 and then going down with the same trajectory and curve. The starting point is not really what matters. It's about the trend, and that would be that the slope of the tangent is increasing in the negative direction. Let's actually take a second to write a couple of things about these graphs. We'll say here first, position versus time graph, regardless of where it starts, should show a slope which is equal to the object's velocity, which is increasing in the negative direction. Slope of the position versus time graph has to increase in the negative direction because the slope is the velocity. The velocity versus time graph should start from 0 if the object starts from rest, which it almost always does, and have a slope which represents the acceleration, which is constant and negative. And of course, we actually know the value, negative 9.8 meters per second squared. And the acceleration graph should be constant, we'll just say. The acceleration versus time graph should be a constant negative value, which is negative 9.8 meters per second squared. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, just real quick before we wrap this up, we answered a question where we were talking about air resistance. And so if we reflected the motion of the object when it was experiencing air resistance, it would look something like this for a velocity versus time graph. And so notice after the first second, the velocity goes up by just under 10 meters per second. But as it continues, and by it I mean time, as time continues, the velocity is increasing, but it's increasing by less and less and less each second until, notice, it stops increasing at all. Take a second to sketch this graph. And when you hit play, we'll write a little explanation. Okay, so I just want to highlight this. This constant velocity that the thing reaches is called the object's terminal velocity. And what we can say about that is that the force of air resistance is actually directly proportional to the square of the object's velocity. And so we'll just write down here, force of the air resistance is proportional to v squared. This means that as the object gets faster, the force of air resistance actually gets larger, which reduces the object's acceleration. And the acceleration gets smaller and smaller and smaller and smaller until it eventually becomes zero, which means that the object just goes at a constant velocity. This constant velocity is called the object's terminal velocity. And just for reference, for a human skydiver with no parachute, the terminal velocity is somewhere between 50 and 60 meters per second, which, if you convert it to miles per hour, is about 110 to 130 miles per hour. So pretty fast, but you're not just going to accelerate indefinitely if you're dropped from high enough. The force of air resistance gets larger and larger and larger as you get faster and faster and faster until you eventually stop accelerating. All right, take a second to pause this video and write that down. And when you hit play, we'll move on to objects thrown up in the air. Okay, and that brings us to objects thrown straight up in the air. Now, there's really two things we need to say about objects thrown straight up in the air before we start. And those two things are, first, even though in these problems the objects won't be starting from rest, they're still technically cases of free fall because the only force acting on the object after they're released by the person throwing them is gravity. And the main note here for this problem is that this is the problem the sign convention really matters for. Take a second to pause this video here and write that down, and when you hit play, we'll talk about how to approach this problem. Okay, so to warm us up for this problem, the case of objects being thrown straight up in the air, we're going to look at 4 examples of motion for an object. We're going to call them case A, case B, case C, and case D. And the question that I'm going to ask you is, what is happening to the object? And so in all these cases, it'll just be like a box or something. And we'll be given information about the box. So the information about box A is the direction these two vectors are acting. That would be the initial velocity and the acceleration. For case B, the direction of the initial velocity and the acceleration. For case C, the direction of the initial velocity and the acceleration. And for case D, the direction of the initial velocity and the acceleration. The question here is, what is the object doing? Take a second to pause this video here and answer that question, and when you hit play, we'll go over it. All right, so this is not new information. In case A, the object here has an initial velocity that goes to the right and an acceleration that goes to the right. This object is speeding up. Case B, this object has an initial velocity, which is to the right, but an acceleration which is to the left. This object is slowing down. In case C, this object's initial velocity is to the left, but the acceleration is to the right. This object is slowing down. And in case D, the acceleration and the velocity are in the same direction. So this thing is speeding up. So why am I showing you this elementary example? Because the whole reason why we've been talking about this so far is to get to this problem. Because you have to be very careful with the sign for this problem. For an object thrown straight up in the air problem, we have to consider 3 segments of the trip. And those 3 segments of the trip are the way up, when it's at the maximum height, and the way down. So, let's talk about the way up first. On the way up, because the object is going up, and the velocity, initial velocity of the object tells you the direction it's traveling, the initial velocity is positive. But because the acceleration is due to gravity, and that always points toward the center of the Earth, the acceleration due to gravity is down. And that means on the way up here, this object is slowing down. Notice here, because this object has gone up, its position is positive, and its displacement is positive. Right? Because its position, we have to consider where we're going to call x equals 0. And for this problem, we might as well call it the starting point here, the ground. And so it's above that, so the position is positive, and it's displaced above that, and so the displacement is positive. And this object goes up until it reaches the maximum height. And when the object reaches its maximum height, the velocity is 0. It stops. Now, a lot of people don't buy that. So I actually want to show that here for a second, very quickly. So notice here, if I open this in QuickTime, not only can I play the video, but I can also analyze it frame by frame. So notice the object goes up until it stops. Then it comes back down. Now, it's kind of hard to see that it stops unless you do it frame by frame. So notice I'm advancing the frame forward every second, and right there, I don't know if you can still hear me hitting the keyboard, tapping the frames forward. It's not moving right there. Now it starts to come back down. There it goes. And so the object truly does stop for a brief instant at its maximum height, because this is where it turns around. And because gravity is still pulling it down to the ground, the acceleration is negative still. And still at this point, the position is positive, and the displacement is positive. On the way down, Now, since it's heading down, the velocity is negative. The acceleration is negative. That tells you this thing is speeding up. And the position is still positive, but the displacement is actually decreasing. It's still positive overall, but the displacement is actually decreasing as it goes back down because it's getting closer to its starting point. All right, take a second to pause this video and write any of that down if you haven't already. And when you're done, we'll go ahead and take a look at a problem. Okay, this question here says a baseball is hit almost straight up into the air with a speed of 25 meters per second. Estimate how high it goes, and B, how long it is in the air. Let's just address C quickly before we begin. It says, what factors make this an estimate? What do you think? Why do you think this problem says estimate, like the last one did? This problem says to estimate because we are assuming that air resistance is not a factor here. But for a baseball, it probably is. And that's an important thing to realize. Now, for this problem, it says here the baseball is hit almost straight up into the air, and the first part is to find how high it goes. So let's address that now. Now, for this problem, they give us the initial velocity, and for part A, they ask us how high it goes. Let's address that now. Okay, so notice what seems weird about this problem a little bit is that the only thing they tell us is that the initial velocity is 25 meters per second. But of course, it's also important to realize in all of these problems, we always know the acceleration, and that's 9.8 meters per second squared. Additionally, because they are asking how high it goes, the initial state, so to speak, of the object is when the ball just gets released by the bat, essentially, just after the ball stops making contact with the bat. But the final state of the object, because they are asking us how high it goes, final state of the object is at the maximum height. And as we said here, at the maximum height, the object's velocity is 0. And so that means for these problems, when they ask us for the maximum height, anything about the maximum height, the final velocity is 0. And we're asked for the maximum height, delta x. Looking at the list of variables, it should be clear they didn't give us time. They haven't yet asked us for time. That the equation we're going to use is the only equation without time, the time-independent equation, vf squared equals v naught squared plus 2a delta x. And when we solve this equation for delta x, we get vf squared minus v naught squared over 2a. And when we plug in the variables here, we get delta x equals 0 meters per second, whole thing squared, minus 25 meters per second, whole thing squared, over 2 times negative 9.8 meters per second squared. 25 squared is 625, and 9.8 times 2 is 19.6. And so when you divide those numbers, you get 31.8877551, which we'll call 31.89 meters. But because the number given in the problem is given to 2 sig figs, that's 25 meters per second, we'll go ahead and we'll call this 32 meters. And that's it for part A. Part B asked us how long is it in the air. Now, to find out how long it's in the air, we have to recognize a very important fact about this problem. And that is that the motion of an object thrown straight up in the air is, as I call it, symmetrical. The acceleration on the way up is the same as the acceleration on the way down. The distance on the way up is the same as the distance on the way down. And so because the acceleration and the distance on the way up and the way down are the same, the change in velocity on the way up and the way down is the same. And since all those things are the same, that means the time is the same on the way up and the way down too. And so this means that the velocity the object has when it strikes the ground has the same magnitude as the launch velocity. The only difference, of course, is the sign. And it's important to note here that this fact can be used to solve for the total time in one step. And I actually want to go ahead and show it both ways here. So let's go ahead and do that. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, let's do it the least conceptually taxing way first. So they told us here that the initial velocity is 25 meters per second. And we know the final velocity, 0 meters per second. We know that acceleration is going to be negative 9.8 meters per second squared. And we're looking for the time. It should be clear to everybody that the equation we're going to use here, because we have V naught A, VF, and we're looking for T, is V final equals V naught plus A T. And when we solve that for the time, we get V final minus V initial over the acceleration. And because the final velocity is 0, we can just go ahead and cross that out right off the bat. And that gives us the time is the negative of the initial velocity over the acceleration. And so plugging that in here, and I'm just going to do this here because I'm running out of room, that gives us negative 25 meters per second over negative 9.8 meters per second squared. Now notice here, the key advantage to that is, of course, the negative divided by the negative is going to give you a positive number, and 25 over 9.8 is 2.55 meters per second, 2.55 seconds, which we'll call 2.6 to 2 sig figs. That's not the answer, though. That is the time to the max height. That's not what they asked us for. What they asked us for was the total time in air. And the total time in air is just double that. Because if it takes 2.6 seconds to come up, it takes 2.6 seconds to go down. And so we're going to say here, T total, the total time, is 2 times T max. And that would be 2 times 2.6 seconds. And that's going to give us a total time of 5.2 seconds. And so that's one way to do it. It works. It's a reliable way to do it. But another way, which we can skip all this, is to recognize that the launch velocity is equal to the negative of the landing velocity. I'm going to show this over here. If you throw this thing up at 25 meters per second, it decelerates for 2.6 seconds until it stops at the maximum height. and then it comes back down. And because it accelerates for the same time and the same distance with the same magnitude of the acceleration, by the time it gets back down to the ground, the speed is changed by the same amount, so the final velocity is just going to be negative 25 meters per second. And the way that I write that usually is that v launch is equal to the negative of v land. That's not a real equation, though. I just made it up. Easy way to remember it, though. And so if we call the initial velocity 25 and the final velocity negative 25, hopefully we'll be able to see what's going on here quickly. Of course, the acceleration is negative 9.8 meters per second squared. And so we have v final equals v initial plus at. And when we solve that for t, we get v final minus v initial over a. Look familiar? And that gives us v final negative 25 meters per second minus v initial 25 meters per second over the acceleration, which is negative 9.8 meters per second squared. Now, this is the part that you need to notice. Look at the numerator here. It's negative 25 minus 25, which is going to give you negative 50 over 9.8. In the previous version of this, when we did the math, we had negative 25 over negative 9.8, and then we had to multiply it by 2. Notice here that we are finding the total time in one step simply because the numerator in this new calculation is double the size of the numerator in the old calculation. And so when we take 50 divided by 9.8, we get 5.10. So we'll call it 5.1 seconds. Now, of course, you may be wondering, why exactly is it 5.1 and not 5.2? It's just a matter of sig figs. If you remember, I said here, the time comes out to 2.55 seconds. But of course, to round it to 2 sig figs, we had to call it 2.6. Of course, if we just doubled 2.55, we would get 5.1. Again, this is not something you should worry about that much. That's actually why I like to use this as the first example. So you realize that it's not that big of a deal. If you showed this on the test, your answer is 5.2, you get full credit. If you show this on the test and your answer is 5.1, you get full credit. We're not going to go all that nuts about rounding for textbook problems. But that's it. This point is very, very, very important to realize. The motion of an object thrown straight up is symmetrical. Since the acceleration, the distance, and the time are the same on the way up and the way down, I should say on the way up and the way down, the velocity, the object, the velocity the object has when it strikes the ground has the same magnitude as the launch velocity. This fact can be used to solve for the total time in one step. Obviously, how you do that and what you choose to do depends on the nature of the problem. That's something you're just going to have to figure out as you go along, depending on what exactly they're asking. Take a second to write this down if you haven't already, because this point is very important and useful. Okay, and so to wrap this up before we go here, we've got one last thing to discuss, and that is what the graphs look like. So let's go ahead and take a look at those graphs for an object thrown straight up in the air. This is what the graphs look like. And notice this should make a pretty good amount of sense here based on the rules for graphing, starting with the position versus time graph. Notice the position versus time graph has a slope which is equal to the velocity. The object goes up, then stops at the max height, and then goes down. So when the velocity is up, the slope of the tangent line has to be positive, which it is, but then the slope of that tangent line gets smaller and smaller and smaller until it eventually becomes 0 at the maximum height. Then on the way down, the slope increases in the negative direction. This is why it has to be an upside down parabola, because that's the only way it can show positive velocity, but decreasing, then a zero velocity, and then an increasing velocity, but in the negative direction. Moving on to the velocity versus time graph, there are a couple things we can say about this. The first is that, as we just said, the velocity has to be positive, then zero, and then negative, which it is, clearly shown on the graph. But I think the more important thing here is that the slope, which represents the acceleration, is constant and negative. And since the slope is the acceleration, it should be constant and negative, because the acceleration due to gravity is a negative 9.8 meters per second squared. Let's just go ahead and summarize that, and we'll call it a day. And so we'll say here, position versus time graph must be an upside down parabola. Since the slope is equal to the velocity, the object's, or let's just say the graph, shows a positive slope, which is decreasing in magnitude on the way up, a zero slope at the maximum height, and a slope which is negative and increasing on the way down. We can say the velocity versus time graph shows a constant and negative slope, which represents the acceleration, because the acceleration due to gravity is constant and negative. Let's just say also the velocity is shown on the y-axis to be positive and decreasing, and zero at the max height, and then negative and increasing on the way down. And lastly, the acceleration versus time graph shows a constant and negative acceleration the whole time. Take a second to pause this video and write that down. All right, guys, that's it for today. Tomorrow, we will apply some of this stuff to some more complicated problems and take a look at a new way of thinking about how we can use these equations to answer some different kinds of problems. Take care, everybody.